This is Chapter 2, Section 2.3, Functions and Relations. Our objectives in this section is to determine whether a relation is a function. That's one of the major ideas. Apply a function notation. Determine x and y intercepts of a function defined by y is equal to f of x. Determine the domain and range of a function and interpret a function graphically. So, a definition of a relationship is a set-ordered pair xy is called a relation in x and y. The set of x values in the ordered pairs is called the domain of the relation, and the set of y values in the ordered pair is called the range in the relation. Practice 1. For the table shown, write the set of ordered pairs that define the relation, write the domain, and write the range. So for our ordered pair, we have xy, and for each of these ordered pairs, we can write it as parentheses with the ordered pair where x is first and y is second. And so now you can see that for the domain of these ordered pairs, we have 3, -2, 5, and 1. For the range set, we have a -4, a 0, a 3, and of course the last 0 is already included. A function is given in the relation of x and y. We say that y is a function of x if for each value of x in the domain there is exactly one value of y in the range. This means that for each x that we find, so for each x, there's exactly one y. So in this case, we have a straight line, which is in the red, over the xy intercept, and we see that for each value of x in our particular line, there's only one value of y. In practice 2, we determine if the relation defines y as a function of x. So in part A, we just put the points in on the xy coordinate system, and we see that for each value of x, there is only one value of y. So for A, it is a function. So now we'll look at for B, and we again, our points are in red for part B, and we see for the -3, we have two values of y for a value of -3. So therefore, this is not a function. It is not a function for this ordered set of pairs. In example 3, we determine if the relation defines y as a function of x. And so for each x, we see we have just one value of y, regardless of what the symbol is. We can put any number in for x and get the same number for y. This is a function because for each value of the domain in x, there's only one value in the range of y. So our examples 6 through 8 determine if the relation defines y as a function of x. So we can write this function, x is equal to 7 minus y, as a line, which we did down here at the bottom, And we can draw that function on the coordinate system. And when we do that, we see that for each value that's on the line for x, there's only one value of y for that line. Therefore, number 6 is a function. Again, for number 7, we can rewrite it as y squared is equal to 7 minus x. And now y is equal to plus or minus the square root of 7. When we graph that function, we see that the function is on its side, right? So it looks kind of like this. Actually, it's more like a parabola, I think, more than anything else, right? But it's on the side. And you can see for each value of x, there are two values of y for number 7. So guess what? This is not a function. For number 8, we have a cubic. We let y, we solve for y, and we get here, we get y cubed is equal to 7 minus x. But we can take the cube root of everything, and we get this function that starts to look like a snake around 7, right? It hits the x-intercept is right at when x is equal to 7. And in this case, for each value of x, there's only one value of y, so in case number 8, we have a function. So to test if a function exists as a function, we can perform what's called the vertical line test. And we do that on a graph. So a graph defines y as a function of x if no vertical line intersects the graph in more than one point. So you can see that our lines, our red lines, are our vertical test, and our function is in blue, and you can see that no matter where I put the red line throughout the function, it only intersects the graph, the function, at one point. Therefore, it is considered a function. That is called the vertical line test. So in examples 9 through 11, when we draw the line straight through the function, for number 9, we see that in fact it's a circle, and we can draw a line through any part of the circle. It is not a function. For number 10, no matter where we draw the line test, we can see that it is a function for number 10. And number 11 is kind of a curious one because it stops there at 5, and we're not sure whether or not the value at 0, when x is equal to 0, where it is exactly. If it has a point, 2 points, then it is not a function. If, in fact, it has, say, a point here at minus 5 and an open-end circle here, then it is a function. But if they're both connected, then it's not a function. So in this case, we're going to say this is not a function because at 0, we can't tell whether or not there are two values for y. So in our practice 3, we determine if the relation defines y as a function of x. So again, we draw the line test, and we see that for part A, we do not have a function because for x equals 1, we get y is equal to 1 or y is equal to a negative 1. So in B, when we draw the vertical line test, we see that we only hit the graph, the function, at just one point. And then finally, we can see in C that there are 2 points at negative 2. So when x is at negative 2, we have a function at we have y is equal to 4 or y is equal to 2. Well, that's not a function because there's two values of y for a value of x. So now we look at practice skill 4. Determine if the relation defines y as a function of x. So I went ahead and graphed the functions. I looked at a and I graphed the functions and I see 3 points. For each value of x, there's really only one value of y. It's 4. So if I could draw, if I had all of the points of x equal 4, it would just be a straight horizontal line. And that is, by the way, a function. In number b, I see that the absolute value of y plus 1 is equal to x. When I draw that function down here, I see that the function looks like this, right? So I have these straight lines going as an absolute value going in the positive x direction. When I draw a straight red line through any point of that function, I can see that for each value of x, there's two values of y. So therefore, b is not a function. B is not a function. And of course, c is our line. We have a center at 0, 0, and the radius is 5. When we draw the function, it's a circle. And a circle, of course, is not a function. Is not a function. Our second objective is to understand function notation. So we're going to evaluate the function f of x is equal to 2x squared minus 3x plus 1 for a given values of x. So we plug in for a f of minus 3 when we put it into the equation, and we just put in the various numbers into the equation where x is, and we solve for x now, and we find that f minus 3 is equal to 28 in part A. So f minus 3 is equal to 28. So now we go to b. We look at b, f of the square root of 2. We put the square root of 2 into our function, and we find that f of square root of 2 is equal to 5 minus 3 square root of 2. We just put in the square root of 2 into our function, and you can see that 2 square root of 2 squared is just 2 minus 3 square root of 2 plus 1. So 4 plus 3 square root of 2 plus 1, and we combine the ones, right? So now x can be a variable. So when we plug the variable in, for c, we have f of a, and f of a is going to be just 2a squared minus 3a plus 1. And then finally for d, we have f3 plus z. When we put that into the formula, we have to expand. So we did that expansion. And then after the expansion, we did the distributive property for 2. And then finally, we combine like terms, and we get f3 plus z is equal to z squared plus 9z plus 10. So in practice skill 5, we have the function h of x is equal to 4x minus 3 for the given values of x. We want to evaluate the function. So for part A, when we put 3 in, we get a negative 15. You may want to practice this yourself. For B, we get a negative 7. For C, we get a negative 3 because h of 0, when we put 0 in for x, we just get negative 3. When we put h of 1 in, we get 1. And finally, when we put h n of 3, we get 9. So please practice these. In practice skill 6, we're going to put in variables into our equations. And so here for mx is equal to x squared plus 4x, for the given values of x, we put in t. And for part A, we just get m of t is equal to minus t squared plus 4. And when we put in a plus h, we get ma plus h is equal to a minus parentheses a plus h squared plus 4 parentheses a plus h. We do our expansion, and our final answer is ma plus h is equal to a minus a squared minus 2ah minus h squared plus 4a plus 4h. Objective 3 is finding intercepts using function notation. So given a function defined by y is equal to f of x, the x-intercepts are real solutions to the equation f of x is equal to 0, and the y-intercept is given by f of 0. So in our first example, 14, find the x and y intercepts. So we let 0 for the x-intercepts. We let 0 is equal to x squared minus 4. We see that's factorable. So 0 is equal to x plus 2, x minus 2. So the intercepts are at x equals minus 2, x equals 2, and we can write the intercepts as a minus 2 comma 0 and 2 comma 0. Now we can put those x-intercepts on a graph, which we see there, where we put it at minus 2 and 2. They're on the x-axis. And now we can find the y-intercept. The y-intercept is where x is 0, and when we put x is equal to 0, we see that y is equal to a minus 4. So the y-intercept is at 0 minus 4, and that's at the vertex of this parabola, it turns out. And so there's our parabola with the y and x intercepts. In practice 7, we find the x and y intercepts of the functions defined by f of x is the absolute value of x minus 5. So for the intercepts, we let 0 is equal to the absolute value of x minus 5. That means that the absolute value of x is equal to 5, so x can either be a 5 or a minus 1. So our x-intercepts are at 5 and at minus 5. And now we find the y-intercept. So we put 0 in for x, and we get y is equal to a minus 5. And so that is the vertex of our absolute value. And we can see that those are our x and y intercepts graphically as well as algebraically. Objective 4 is determine the domain and range of a function. Given a relation defining y as a function of x, the domain is the set of x values in the function, and the range is the set of y values in the function. So here we can determine the domain in example 17. If we look at our graph, we see that the domain is really all real numbers. X can be any number along the x number line. So in interval notation, we have a negative infinity to infinity. Now, the range, of course, is our values that y can take on, and so it turns out that y can only go from a 2 to infinity. So in interval notation, we have a parentheses, or not a parentheses, a bracket, a closed bracket, 2 comma infinity. notice that the bracket is telling us that 2 can be equal. It can be equal to 2, and it can go on up to an infinite number. In example 18, here we have a discontinuity, but even in this discontinuity, we can find the domain and the range of the function. So here, the domain, it turns out to be, again, all values of x. So along the x-axis, it can go in either direction, so it goes to a negative infinity to infinity. And we check to see what our y values can be. In this case, y can go start at a minus 10 actually and go on up. So our range is the enclosed bracket negative 10 comma infinity. I wanted to show you a lot of examples, so here's example 19. Determine the domain and range for the following functions. Again here, the domain though, we've ended x at 4. So x can be 4, right? But now it takes on all the values of x in the negative direction. So the domain is negative infinity to 4. For the range values though, the range is very limited because it really is at 1 to 8. So I have bracket 1 comma 8. Here's an interesting one, example 20. Determine the domain and range for the function. So when I look at this function, I see that the function kind of begins over here at a negative 2 for x. So it starts here at a negative 2 and it goes in the positive direction, it appears. So we have bracket negative 2 comma infinity. For the y value, however, y doesn't get above a 4, but it appears that it goes completely down in the negative direction. So we have parentheses negative infinity comma 4 bracket closed. In our practice skill 8, determine the domain and range for the following functions shown. So you'll notice in part A we just have points, and when we only have points in our coordinate system, we just represent those as set notation. So the domain for A is just the points that represent the points in space, which is minus 4, minus 2, 0, 3, and 4. Those are the x values. And the range values then are just those that are on the y values, which is minus 3, 0, 1, and 5. For part B, however, the domain can be put in interval notation because it's on a continuum. And here we have a minus infinity to 4 because x goes to 4 and in the direction of a negative infinity. And then for the range, it looks like it starts at a negative 4 and it goes in the positive direction. So again, we put these in interval notations and you can see how they are done. In practice skill 9, we're only going to look at domains because we're going to look at which functions have restrictions and which functions don't. So the domain tells us if x has a restriction. So if we look at part A, we can see there is a restriction on the function in A where we have f of x is equal to x minus 2 divided by 3x plus 1. The domain has a restriction at x cannot equal a negative 1/3 because we can't divide by 0. So from set notation, set builder notation to interval notation, we can show you that A has the domain of a negative infinity to a negative 1/3 union 1/3, negative 1/3 to infinity. Number B, on the other hand, doesn't have any restrictions. X squared does not have any restrictions either in the positive or negative direction. So guess what? It's all real. And here's our notation for the domain for B. For C, we see that in order for k of x to be real, we do have a restriction. It can't be less than a negative 3, so x has to be greater than or equal to a negative 3, and there is set builder notation, and there is interval notation. And finally, in number D, there are no restrictions on x, so it's all real numbers again. So now we're going to interpret our function graphically. So that's our objective 5. We see in this case that there is a discontinuity at 1 and negative 1 for y. So at negative 1 for x, there's a discontinuity. But in any case, the function itself, if we look to say, okay, what is the evaluation of f of minus 3? If we go to where minus 3 is, which is my little red dot here, we see that f of minus 3 is minus 3. F of 0, right? So I go where f of 0 is, and it's right here. So f of 0 is equal to 2. So now it says use the graph of y equals f of x to answer the following questions. Find all of x for which f of x is equal to a minus 1, and we look across where a minus 1 is. Here's minus 1, and we see that the only value of minus 1, f of x is minus 1. We see it's x is equal to a minus 1. Find all x for which f of x is equal to 1. Well, again, when x is equal to when f of x is equal to a 1, which we're along this value here, we see the open-ended one, but in this case x is equal to 2, right? So that's the answer for this one here. X is equal to 2. So now we're going to use the same graph again and determine the x-intercepts. Are there any x-intercepts? Well, no, because the graph never touches the x-axis. So there's no x-intercept. Right? There's no x-intercept at all. Is there a y-intercept? Well, yeah. Where does the function cross the y-axis? It's there at 2. Right? There's where the y-intercept is, and it's at 0, 2. Now we're asked to find the domain of f, and so we look and see, well, it goes, all values of x can be put into the function, it looks like. So all real numbers can be put in. Now it says determine the values of y. We see that there's a small discontinuity between negative 1 and 1. And so we have to write that in our notation. So determine the range of f. It is a negative infinity to a minus 1, bracket closed, union of bracket open 1 to infinity. You should probably try to do practice skill 10 on your own. We'll just give you the answers. You can look at the function of the graph. You can see that f of minus 2 is at 1. So when we go to minus 2 and we go up, we see that it's at equal to 1. When we see f of 4, we see when we go to where x is 4, we see we have a open end, so there's no solution. That's an empty set. There is no solution. all values for which f of x is equal to 3, we can see where we go to 3, we see that x is minus 4. So here's where that is, right? All x for where f of x is equal to 1, we see it's at this interval right here. So we can put that interval value here. The intercepts, well, where does it cross the x-axis? Right here. The y-intercept is at the same spot. The domain, it goes from 4 to all negative values. So that's where I have the interval negative infinity to 4. And then the range values go from 4 to a positive infinity. So there's my range values there. Well, this concludes our chapter 2.3 on functions. Please practice some of the lecture notes, and we'll discuss this more in class.